In this video, we'll take a look at the no-load characteristics of transformers. Here we have a very simple two-winding transformer with the secondary winding not connected to any load, and the primary winding connected to an AC voltage source. So what would happen after that? So the first thing that will happen is that the primary winding will draw a current. We call that current the exciting current, and that current will be periodic, as it will follow the periodic nature of the applied voltage. However, it won't be sinusoidal, and I will explain later why it will not be sinusoidal. So this current will produce a flux inside the magnetic circuit. So a flux will flow within the ferromagnetic core. And what is interesting here is that the flux will be actually sinusoidal. And I will explain later again why it will be sinusoidal. These form flux will link both the primary winding and the secondary winding. And on the primary winding, an induced voltage E sub 1 will be developed across that winding uh, with a value in accordance with the Faraday's law. So the induced voltage there will be proportional to the number of turns in the primary winding and the rate of change of the flux linking the primary winding at any given time. Take note that the same flux also links the secondary winding, and therefore a voltage will also appear here at the secondary winding. So let's call that E sub 2. Because the primary side is a closed circuit, we can apply Kirchhoff's voltage law, and this is the equation based on KVL. Take note that the applied voltage will be distributed not only uh, to the induced voltage, but also across the resistance of the primary winding, and another term we call the inductive reactance. Now, the inductive reactance here is due to the primary winding leakage flux. Yes, some of the flux that will be produced inside the magnetic circuit will not be entirely inside the magnetic circuit, but a small amount will be escaping the magnetic circuit and is considered as a leakage flux. And that should be considered in our KVL equation because this leakage flux also produces an induced voltage in the primary winding. Now, in large transformers, the resistance is very small, usually very small, owing to the large conductors that is used in the primary winding, and the leakage flux there is negligible compared to the total flux inside the magnetic circuit. Because of that, uh, we can actually say that V sub 1, or the applied voltage, is roughly equal to the induced voltage due to the primary flux inside the magnetic circuit, and that can also be formulated using phase source. Here we have an illustration of the nature of the leakage flux. So when current enters the primary winding, a flux is produced, and most of that flux actually is formed inside the magnetic circuit, but a small amount also leaks out of the circuit. So this is the leak, leakage flux here, and the main flux, the one that is inside the magnetic circuit, also links the secondary winding. Now, if this secondary winding is drawing current, because let's say there is a load connected there, uh, the secondary winding will also exhibit a leakage flux there. So we call that P sub S, leak. So in a real transformer, the total flux produced by the current in the primary winding is actually made up of the main flux, main mutual flux, because it also links the other winding, and it is confined entirely inside the iron core, plus a small amount of flux we call the primary leakage flux, which only links the primary. This leakage flux in the primary uh, will induce a voltage, a small voltage. It's called that E sub PL, and that can be and that will be proportional to the amount of current that flows into the primary winding. So we can formulate this as this one. Okay, so the voltage due to the primary leakage flux is the primary current times the um, reactance due to the leakage flux. Now let's assume for the moment that after connecting the primary winding to a sinusoidal source, a flux is formed inside the core that is sinusoidal, and that flux is given by this expression. By Faraday's law, we can compute uh, the induced voltage due to this flux, and it is given here. We can also compute for the RMS voltage. We can solve for the maximum flux, and that is given by this expression here. And we notice that the maximum flux is simply due to the applied voltage. Therefore, we can say that uh, the flux is merely dependent on the applied voltage. And it's not even shown here that the flux is dependent on the exciting current. So this flux is sinusoidal based on this expression, and this sinusoidal nature of the flux must be satisfied by the exciting current, because it is this exciting current that produces this flux. So this current must adjust itself so that the flux will be sinusoidal. Now, in my previous materials, it is explained that the flux is not actually proportional to the exciting current because of the saturation of the magnetic core, such that for higher values of flux, we need a much higher value of current to produce that flux. Let us show the relationship of the applied voltage, the exciting current, and the flux in terms of waveforms and phasor diagrams. So here we have the applied voltage that is roughly equal to the induced voltage and shown here as a sinusoidal waveform. The corresponding phasor is shown here. Now, here we have the flux form inside the core, and the flux is also sinusoidal, but it is leading the applied voltage by 90 degrees. Um, if you go back to our previous slide, you'll notice that that flux is actually leading the applied voltage by 90 degrees. And since it is leading, we therefore draw the flux phasor as this. Now this is how the exciting current looks like. So it is periodic, but it is not sinusoidal. Notice that for higher flux here, the exciting current tends to be sharper uh, at that point because the the core is more saturated compared if it is lower, if we have a lower flux, and therefore the exciting current has to be higher in order to overcome that saturation and produce a higher flux inside the core. The exciting current is non-sinusoidal but periodic, and because of that, it can be expanded in terms of a series of sinusoidal functions based on Fourier series. So that current can be represented by a fundamental component and its harmonics. Now, if a transformer is operating at full load, this exciting current is actually uh, small compared to the full load current, and therefore we can actually ignore these harmonics. Exciting current, although non-sinusoidal, can be represented by an equivalent sinusoidal current, provided it has the same RMS value, frequency, and average power as the actual exciting current. And because of that, uh, using the equivalent sinusoidal exciting current, that current can be resolved into two components. We have I sub C that is in phase with E sub 1 or the applied voltage, and another component I sub M that is lagging the applied voltage by 90 degrees and in phase with the flux inside the core. Therefore, we can show the exciting current as a phasor that is lagging the applied voltage. So take note that this is approximately equals to the applied voltage. It is lagging that voltage by an angle theta sub c, but leading the flux P. Now I sub m here is can be considered as the component that supplies the current, we call it the magnetizing current, that is needed to produce the flux, while the component I sub C is the component that will supply power to answer for the losses inside the transformer core. These losses are the hysteresis and the eddy current loss. So we call this the core loss or P sub C. Thus, we can compute P sub C as the applied voltage times the exciting current times the cosine of the angle between the applied voltage and the exciting current. And that can be, and that is only applicable for single phase transformers. A datasheet is actually available when buying transformers, and that is shown here in this datasheet for a given magnetic flux density inside the core. So take note, magnetic flux density is equals to the flux inside the core divided by the cross-sectional area of that core. So if we are given the maximum or the flux density inside the core, we can actually compute or we can actually determine from the data sheet the core loss in watts per kilogram of the transformer core. Now this data sheet here is shown for an M5 grain oriented electrical steel with the specified thickness and for 60 hertz applied voltage. There is another data sheet where given again the magnetic flux density inside the core, we can get the what is called the exciting RMS volt amperes drawn by the transformer in terms of volt amperes per kilogram of the transformer mass. Let's have an example to illustrate some of the concepts that we have discussed. So here we have a transformer with a primary winding made up of 200 turns. This winding is wound to an M5 grain oriented electrical steel. The winding is connected to a 60 Hz voltage source, producing a flux inside the core with a flux density equals to this. The steel occupies 94% of the cross-sectional area of the core. So let's say this is the cross-section of the core. So the area there is A sub C. 94% of that area is actually steel. Okay, so this is due to the laminated nature of the transformer. The mass density of the steel is given, and we're asked to find the core loss component and the magnetizing component of the exciting current and the power factor for this no load condition. So here, based on this maximum flux density of 1 Tesla, we can find the core loss per kilogram from the data sheet. So it's 0.5 watts per kilogram, and the exciting volt amperes at zero point 0.6 volt amperes per kilogram. The weight of the transformer is given. So let's proceed to the solution. So first, we compute for the uh, induced voltage in the primary winding. So we know this to be roughly equals to the applied voltage. Now we can get this because we're given by the flux density. So we multiply that by the uh, cross section of the steel, we get the flux. Okay, so here is the number of turns. This is the actual area of the core. We convert that to square meters and we reduce that by 6%. Then we get the derivative of the flux density, and that should give us this induced voltage. So the induced voltage is actually leading the applied the flux density by 90 degrees. So we can get the RMS value of this voltage, and that should give us this figure here. So this is actually approximately equals to the applied voltage here. So we're given by the core loss per kilogram and the exciting volt amperes per kilogram and the weight of the transformer. We know the exciting volt amperes to be, so the exciting volt amperes per kilogram can be equated to this expression here. So this is the applied voltage times the exciting current divided by the total weight of the transformer. And from this, we can solve for the exciting current, and that should give us this result here. We can compute for the total core loss. Uh, so we're given the core loss per kilogram times the total weight or the total mass of the transformer, and that should give us 6.6 watts. But we know the uh, total core loss to be equals to this. And from here, we can compute for the phase angle between the applied voltage and the exciting current. There we can get the phase angle. Okay, so this is the phasor diagram of the quantities. From there, we can compute for the core loss component of the exciting current because we already have the exciting current, the magnitude of the exciting current, and the phase angle. So therefore, we can get this. So that will give us this much core component. So this is the current that is responsible for the core loss. That answers for the core loss of the transformer. And we can also compute for the exciting or the magnetizing current from this diagram, and that will give us this much. So that's it for this video, and on our next video we shall discuss the load characteristics of transformers.